Okay, so started this in high-energy cosmic rays using experiments designed by John Simpson's group, using the Pioneer 10 and 11 spacecraft. Was lucky enough to participate in the first flyby of Saturn with Pioneer 11. But the original plan was to become an architect. That obviously didn't work out. I pivoted into radio astronomy as a graduate student and have been working in solar radio physics, some side interests in solar wind turbulence, dabble in various stellar radio emitters, chemically peculiar stars, magnetic cataclysmic variables, lake-type dwarf stars, and searches for exoplanets. So today, I'm tasked with telling you about radio emission in the heliophysics context, and I sort of can tell you a little about a lot or a lot about a little, and I went with the latter route, hoping to give you sort of the flavor of the kinds of things that are possible using radiation as the vehicle for probing astrophysical, or in this case, heliospheric plasmas of interest. So first, let's begin at the beginning. What do I mean by radio waves? You see many, many decades in energy, in frequency, in wavelength here, all labeled on this schematic spectrum. And what I'm talking about is basically wavelengths longward of a millimeter or so. And it is about 7+ decades of wavelength compared to that narrow slice in white of 1 octave of wavelength for the visible part of the spectrum. But the commonalities here are, first of all, the Rayleigh-Jeans approximation is valid. That is, h nu is much less than kt for radio photons. And there are commonalities in the observational technologies, the instruments that we use, for example, heterodyne receivers to observe radio waves. So everything longward of a millimeter or so, or frequencies less than a few hundred gigahertz, that's what I mean by radio waves. I like to kind of organize things according to this diagram by source of radio emission. It can be either intrinsic or extrinsic. When I say intrinsic, I mean the radio emission arises from the plasma itself due to various microprocesses. It can come from an equilibrium distribution of particles. There we go. That working? Yeah. Equilibrium distribution of particles and various incoherent radiation processes prevail. For example, thermal free-free, that is collisions of electrons on ions, or thermal gyroresonance, gyration in a magnetic field of thermal particles. Or you can have a non-equilibrium distribution, power law tail, due to energetic processes. And that leads also to incoherent radiation, an example being non-thermal gyrosynchrotron radiation, which is mildly relativistic electrons. Or we can have different kinds of non-equilibrium distributions that lead to coherent radiation processes that we've already talked about a little bit, I think, in previous lectures. And so some examples I'll discuss briefly are plasma radiation and cyclotron maser radiation, which is also, by the way, important for stars and possibly exoplanets. But the opposite, we can sort of turn things around and take a radio source as a probe of the foreground plasma. So we can either use a passive source, for example, a background quasar to transilluminate the foreground solar corona, or we can use spacecraft beacons during various conjunctions. So you have essentially a monochromatic signal you can transilluminate the plasma with. And these exploit what I use the broad term propagation phenomena. The foreground medium modifies the transmitted signal in various interesting ways, and examples include interplanetary scintillations, angular and spectral broadening, which I'll talk about, Faraday rotation, which was mentioned yesterday. And then there are active sources. These are typically human-made transmitters. So for example, a radar signal can be used. This I'm not really going to talk about today. They're used heavily in ionospheric and magnetospheric physics. For example, coherent or incoherent scatter radar techniques using Thomson scattering or reflection off of large density and homogeneities. And I'm sure some of you are familiar with these techniques. So that's kind of what we're doing today, mostly concentrating on the top half of this diagram, and time permitting, I'll say a few words about propagation phenomena. So the plan, I'm sure some of these details are familiar to you. For others, maybe not so familiar. Mostly to introduce terminology and some concepts that we use in radiophysics quite often. I'll touch on emission mechanisms, and then I'll go into very briefly the kinds of observations we make at radio waves, and the tools that we use, the instruments, the telescopes we use to perform those observations. Then I'll spend the back half of the talk sort of doing this lightning tour from the low atmosphere all the way out to heliopause of radio emission. And then, as I said, time permitting, something about propagation. So again, you can sort of go to if you're familiar with the 3-volume set on heliophysics based on the summer school over the past 20 years, there's a lecture I wrote in the first volume, which goes through many of these concepts if you don't want to bore yourself looking at these now. But I think you've all seen this before, sort of the elements of radiative transfer. At radio wavelengths, it's fairly straightforward, certainly for the continuum. We can think of radiation as propagating along rays, and sort of looking at this cartoon over here, we define the specific intensity or brightness in terms of energy through a differential element of area per unit time, bandwidth, and solid angle, the amount of energy, differential amount of energy flowing through that differential area. And the units are cumbersome. It's ergs per centimeter squared, per second, per hertz, per steradian. Okay, well, we can retire one of those variables by talking about the flux density or spectral flux density by integrating over all rays incident on that differential area. So we have flux, and that has somewhat reduced units, watts per meter squared per hertz, for example. And at radio wavelengths, we refer to flux density in units of Jansky, named in honor of Karl Jansky, who first detected cosmic radio waves. He was an engineer at Bell Labs nearly 100 years ago in 1930. So it was front page news in the New York Times at the time. So it's a tiny unit. It's 10 to the minus 26 watts per meter squared per hertz. And in fact, modern telescopes can get down to micro Jansky levels, even nano Jansky levels, instruments like the VLA. But the sun is big and bright and bouncy, and it's not a very convenient unit. We use solar flux units, which are 10,000 Janskys. And in fact, we see mega SFU events, so 10 million or 100 million Janskys. So in free space, DIDS doesn't change. You can only change the specific intensity by emission along its trajectory, absorption, or scattering. So let's ignore scattering for now. The emission coefficient is defined in terms of emission per unit solid angle, per unit volume, per unit frequency. And we can sort of reduce that to this term here by noting that DADS is a volume, differential volume unit, and we can specify the change in intensity in terms of the emissivity times the path length, differential path length. And by the same token, we can define an absorption coefficient and write a simple continuum transfer equation. So the change of specific intensity along the path is a function of the absorption and the emission along that path. Now, I'm sure you're all familiar with optical depth, which is just the line integral over the absorption coefficient, and the source function, which is the ratio of emission to absorption coefficients. And we can rewrite the transfer equation in terms of these quantities. And the nice thing at radio wavelengths about a distribution in thermodynamic equilibrium is that it's characterized everywhere by a single temperature, okay? And in that case, the radiation is referred to as black body radiation, and it's described by this function B sub nu, which is purely a function of temperature and frequency, and it's given by Planck's law. Okay, so this form involving the exponential in the denominator, but as I said, the nice thing at radio wavelengths is that we can, since h nu is much less than kT, we can expand the exponential, and we have this very simple relationship between specific intensity and the temperature of the medium and just wavelength squared or frequency squared, whatever your preference is. Nice linear relationship. So we can actually rewrite that transfer equation in terms of brightness temperature, where brightness temperature now is a black body yielding the same brightness or intensity, specific intensity, at the frequency in question as the Planck would, as the Planck function would. And we can define the effective temperature through the source function using the same expression, basically. So now we have a simple transfer equation in terms of optical depth and brightness temperature, which we're very fond of. And for a uniform source with no background emission, just a slab of stuff, brightness temperature is just related to the effective temperature of this very simple expression. And if it's optically thick, it's opaque, we just have the effective temperature is equal to the brightness temperature. And if it's in thermodynamic equilibrium, we have a direct thermometer at radio wavelengths of what the temperature of that material is. That's convenient. And if it's optically thin, then we just have this simple relationship between brightness temperature and effective temperature, and all the microphysics of interest is embodied in that optical depth, which in turn is related to the absorption coefficient. So we hide lots of nasty details in that alpha sub nu, but conceptually it's all very simple. Now in practice, we're interested in resolving the radio emission on the sky, lots of information in imaging. For a telescope, the angular resolution we designate omega sub naught here, referred to often as the beam in radio astronomy parlance. And so we have, if the source is resolved, we have a measure of the radiation flux density per resolution element, omega sub 0. So the flux density is just the specific intensity times the resolution element, or we can turn things around. A good proxy for the specific intensity is just flux per beam. And so you often see units of Janskys per beam when you go to radio astronomy talks. And substituting for I, flux density is related to brightness temperature and the angular resolution by that bottom expression there. So it's all pretty straightforward. I haven't, and I'm not going to talk about polarimetry very much. This expression assumes that we're sort of seeing all of the radiation, both orthogonal senses of polarization, either orthogonal linear senses or circularly polarized senses. Okay, so that's sort of some preliminary vocabulary and concepts. Emission mechanisms. Well, I'm sure you've encountered this. How do you get electrons to radiate? You accelerate them. Okay, and you've probably all seen a derivation of the Larmor formula, which is given there in the top line. And you see that it depends on acceleration squared, and it depends on sine theta squared, where theta is the angle between the acceleration and the velocity vector. They're not necessarily the same, right? So total power and differential power are given by those two top expressions. And as was mentioned yesterday, since ions, specifically protons, are nearly 2,000 times more massive than electrons, you see that all things being equal, electrons are going to be far more efficient emitters than ions. So everything we see at radio waves on the sun is basically electrons being accelerated in one way or another, or non-equilibrium distributions of electrons in the sun's corona, right? Now, that's sort of for the Larmor formulas for non-relativistic electrons. Once we speed them up, you'll see that there's this term in the bottom, and this is referred to as relativistic beaming. You boost to the fourth power, beta is V over C, you boost the emission along the trajectory by this incredible gamma to the 4. So when you're talking about synchrotron radiation for highly relativistic electrons, tremendous relativistic boosting in the direction that the electron is moving. But what are the sources of electron acceleration in the sun's corona? Well, the most obvious one, the most ubiquitous one that happens in all astrophysical contexts is just collisions between electrons and ions. And the most common ion in the sun's corona is the proton, right? Just ionized hydrogen. And so it fuels as it moves along its trajectory here, past some ion, it feels a little impulse acceleration perpendicular to its trajectory, okay? So it sends out a little dipole pattern. And if you have a whole thermal soup of these electrons and ions, you can integrate over the particle distribution function, and you get this somewhat unpleasant looking expression here in the middle for the absorption coefficient, free absorption. And that can be simplified using Gantt factors and so on. And if you go through the arithmetic, you find that for a uniform optically thin source, the brightness temperature in this case is just proportional to the emission measure that we talked about yesterday, not the differential emission measure. This is the total stuff along the line of sight over frequency square over temperature to the half. Okay, so pretty straightforward. So the optical depth due to free increases with the amount of stuff along the line of sight, and it decreases with increasing frequency, and it it depends on temperature, but it's relatively insensitive. It goes as t to the half in this context. What's another source of acceleration? Well, I already mentioned it. Basically, the Lorentz force obliges electrons to execute a circular motion around the magnetic field, as illustrated here. And it does so at the electron gyro frequency, which in units we're familiar with B and Gauss, I'm using CGS for this talk, is 2.8 megahertz times the magnetic field. Okay, so pretty straightforward. Would sort of suggest a straightforward tool for measuring magnetic fields in the solar atmosphere. Now, I've already sort of mentioned gyroresonance emission, gyrosynchrotron emission, even synchrotron radiation. These are just all words for gyromagnetic radiation, where the energy of the electrons in question increases. So thermal gyroresonance emission comes from a distribution in thermodynamic equilibrium. So there we have a radiation pattern in the upper right there. And if you're sort of measuring the electric field as a function of time as a distant observer, you'll see this slightly distorted sinusoid. And because it's slightly distorted, if you take the Fourier transform and make the power spectrum, you can sort of see that there are a couple of low harmonics that are emitted. And this is what we see on the sun. Low harmonics of the gyro frequency for thermal plasmas. And I'll show you some examples. But as we boost the energy, say in a flare, the radiation pattern becomes increasingly beamed. The time variation of the electric field becomes much more distorted. And again, this just indicates that emission is occurring at higher harmonics of the gyro frequency, so much so that they blend into a continuum. This is gyrosynchrotron radiation. And then finally, we don't really encounter full-up relativistic electrons at radio waves, but at higher frequencies, say infrared, maybe. But the fully relativistic gamma, much bigger than 1, we don't really encounter in the frequencies I'm going to be talking about today. So these are both examples. The gyro emission and the thermal free emission are incoherent mechanisms. In other words, it's a single particle doing its thing, and you integrate over a distribution of such individual particles. But you can also have collective effects, nonlinear wave particle interactions that lead to very intense emission that we refer to as coherent radiation. And these occur at the natural frequencies of the system or combinations thereof. And what are the two natural frequencies of the corona? One is the electron plasma frequency, and I'm sure many of you are familiar with Langmuir waves, plasma waves. They're just electrostatic oscillations because they have a finite temperature. They're dispersive in the sun's corona, but they're non-escaping. They have to be converted to electromagnetic radiation to become what we call plasma radiation. And that's sort of illustrated. I'm not going to go into the details because they're quite involved, and I could spend the entire 90 minutes on it, on conversion of Langmuir waves to either fundamental or harmonic emission at the plasma frequency or twice the plasma frequency. If you're interested, the theory goes all the way back into the 50s and has had many iterations and refinements since. I would say the picture here is somewhat outmoded, certainly for fundamental plasma radiation. Processes involving direct conversion of mode conversion of Langmuir waves to electromagnetic waves are becoming increasingly relevant, I think. Let's see, does it show up? Yeah, you can see here the same distribution that Jasper showed you yesterday, basically the so-called bump on tail distribution. So you have a positive gradient in velocity or momentum space. That's the source of free energy that drives this plasma radiation through a two-stream instability. And he showed you that nice simulation of the thing becoming unstable. Okay, so that's one coherent mechanism. Another one that maybe Bob Ergen discussed is the cyclotron maser. So it's basically a negative absorption mechanism, and its attraction is that it's a direct coupling of the free energy available in the particle distribution to electromagnetic waves. For fundamental radiation, the so-called X mode, the extraordinary mode, is favored, and so it has very fast, very direct amplification of X mode waves. And it's thought to be relevant to something called the solar spike bursts. These are very narrow band, essentially 100% circularly polarized, hence because only one electromagnetic mode is being amplified. And these sort of last in 10 milliseconds or so. So the kinds of distributions that can, so bump on tail gives you one kind of positive gradient. You can also get it through a loss cone distribution. So you remove the electrons streaming down to the sun. They precipitate out of the trap, the magnetic trap, reflect, and suddenly you have an upward propagating loss cone, and you get fast amplification of waves in a narrow cone of emission. This is known to occur on Jupiter. It's thought to occur on lake-type stars. It probably is responsible for the spike bursts. I would say that evidence for its role in the sun more broadly is a little bit elusive, but I think it's an important mechanism to keep in mind. Okay, now I'm going to sort of spend a few slides on the types of observations we make. The simplest of all is just measure the flux density at some frequency from the sun. And this has been done for years and years and years. The Air Force in particular is interested in flux density as a function of frequency from the sun for reasons of communication. And the aeronomists are also interested in flux density from the sun, particularly at 10.7 centimeters. You've probably heard of it, F10.7, 2.8 gigahertz. It's been measured at Penticton for decades, and it's used as a proxy for the EUV radiation incident on the top of the atmosphere. Okay, okay, so that's pretty simple. You can just look it up in solar geophysical data, the noontime flux at, say, 1.4 gigahertz, or several other frequencies. And that's done by the Air Force Radio Solar Telescope Network, RISTA. But you can also do more complicated things. You can sort of record that flux as a function of time, make a light curve at a given frequency, okay? And that's also done routinely by the Air Force. You can do a measurement of the polarized flux density as a function of time. So polarimeters are the instrument of choice. And the polarimeters in Japan at Nobayama have been used for many years, or Toyokawa. Let's take it a step further. You can measure the spectrum at a given time, or you can measure the spectrum, the intensity as a function of frequency and time, and make something we call a dynamic spectrum. And that's shown on the bottom here, a nice clean spectrum, so time on the x-axis, frequency on the y-axis, and this is a so-called type 2 radio burst. This has been a workhorse in solar radiophysics since the very beginning, and as I'll discuss very briefly later, the classical radio burst types 1, 2, 3 that you've all heard of sort of were identified using this particular tool. And they continue to be used widely. But we can also image the sun at radio wavelengths. Here's a sampling of images from 21 centimeters on the left to 6 centimeters in the middle, the Nobayama image at 1.7 centimeters, and then finally ALMA, an instrument operating at millimeter wavelengths. That's what the sun looks like at 1 millimeter. You can ask yourself, why is it limb brightened? Ideally, in a perfect world, we'd combine all of these things, all of these observables, time-resolved broadband imaging spectropolarimetry with one instrument. We have a pathfinder that does that partially, that I'll talk about briefly. Instrumentation. All right, well, to do things like total flux measurements, get light curves, do dynamic spectroscopy, these usually just integrate over the whole sun. Just sees the sun as a star. The sun is big, it's half a degree, so to see it, because we're diffraction limited to lambda by d, where d is the aperture, we need little tiny telescopes to see the whole sun. It's just 115 wavelengths, or the wavelength is in centimeters here. To image the sun at radio wavelengths, we need a really big aperture, d, right? So the biggest aperture that used to exist was Arecibo, 1,000 feet, 305 meters. That was occasionally used for solar stuff, but let's face it, a 1,000-foot telescope only gives you a resolution of 3 arc minutes at 20 centimeters. A tenth of the diameter of the sun, which is not very good resolution. So what do we do? Well, it's very elegant. What you do is interferometry. You use many small antennas to effectively synthesize a great big aperture. And the size of the aperture is defined by the distance between the two outermost antennas. So distance between antennas is called a baseline. And ideally, you have lots and lots of small telescopes and lots of baselines, because each baseline effectively measures a Fourier component of the brightness distribution on the sky. And then you use elegant inversion techniques that Farzad has told you about to basically estimate the true brightness distribution based on inversion of the Fourier transform. Okay? So it's a black art, and it's a fine art, and it's been used for decades. Also, I should point out that interferometry at radio wavelengths is developed to the point where we do space-based VLBI. So the Earth is too small. You can use the Earth, telescopes on opposite side to get a very long baseline. Basically, a sufficient resolution to resolve a dime in Los Angeles from New York, micro-arc seconds, but that's still not enough. And so they're now space-based experiments. For the sun, and you can think about this too, we don't need that kind of resolution. It's pointless. But we would like arc-second resolution. Here's some examples of interferometers that have been used to point at the sun on the bottom. In fact, if you look at the VLA in the lower left, you see that the shadow of the quadrupod is pretty much on target. It's pointing at the sun. The Nobayama radioheliograph, lots of little dishes operating at 17 and 34 gigahertz with the Japan Alps in the background in the middle. And then the IATSE instrument that I'll talk about a little bit more is on the right. Okay, now I'm going to go sort of through a rapid tour of the kinds of phenomena that can be observed at radio wavelengths, hint at the kinds of things that we can learn from such observations, but I'm not going to go into a deep dive and go into the details. Feel free to ask questions during the course of this tour. Basically, radio waves occur in all layers of the solar atmosphere, from the chromosphere all the way out to heliopause, the entire heliospheric system. Okay? So I'm going to sort of touch on examples from emission from the quiet sun, the chromosphere, which is relevant to coronal heating, active regions. I'll say a few words, actually quite a few words about flares, energetic phenomena, a few words about coronal mass ejections that you can observe in a couple of different ways using radio waves, radio bursts, and what they can tell us, and then finally go out to the bound of the solar system itself. And I'm going to use this device schematically showing from left to right submillimeter, millimeter waves, all the way to the left where we get to hectometer, even kilometer wavelengths. So we're observing radio bursts and emission from heliopause at just a few kilohertz. So divide, velocity of light by 3 kilohertz, and you get 100 kilometer wavelength is what you can observe out there. The hash vertical line is sort of the 5 to 10, 15 megahertz. That indicates the ionosphere. Free electrons in the ionosphere. The plasma frequency is basically a barrier. We use it at short waves to bounce off, right? Get long distance transmission on the surface of the Earth, but it means that cosmic sources can't penetrate. And so if we want to observe radio emission at very low frequencies, very long wavelengths, we have to go to space-based platforms, okay? So the various telescopes used to observe the sun at these various wavelength regimes are indicated by their acronyms: ALMA, the Atacama Large Millimeter Submillimeter Array; the Jansky VLA; MUSER is a Chinese instrument; Nobayama radioheliograph, now switched off; EOBSA. I've mentioned LOFAR is a low-frequency array in the Netherlands; MWA, Murchison Wide Field Arrays in Australia; LWA long wavelength arrays in Avro, Owens Valley; NARH is the Nancy radioheliograph in France. And then there are a host of instruments flying spectrographs on board, PSP, Parker Solar Probe, the wind satellite, the stereo satellites, and I'll say maybe a word about Sunrise. It's going to be a sort of mini VLA of 6 small antennas flying in formation to do radio burst imaging and possibly heliopause imaging. And I indicate schematically and along the green arrows there, sort of where this radiation at various wavelengths originates, and indicate sort of what the mechanisms are. So it's a very broad, it's a very rich range of things that one can do. So let's look at ALMA a little bit. There's again the image at 1 millimeter. You're basically seeing the low chromosphere to the upper left there, just thermal free emission from the quiet chromosphere. Anybody know why it's limb brightened, actually? I suppose if you look at this image in H alpha, right, in optical, it's always limb darkened. Why the difference? Think about it. The temperature is increasing in the chromosphere with height. And as we go to the limb, you become optically thick at a greater height and therefore greater emissivity. Okay? And that's the opposite is true at H alpha. In the middle there, I'm showing sort of 2 unpublished results. A phenomenon called coronal rain is occurring in that movie in the bottom. So you're seeing, here we're achieving the goal of sub-arc second imaging in the nominal radio regime. A whole lot of work went into that movie because it's a 23-pointing mosaic because the field of view of ALMA is so tiny. And then we're actually doing our first imaging and polarization measurements at 3 millimeters of flares, which is shown on the right there. The upper panel is total intensity and the lower panel is Stokes V, so circularly polarized radiation. And you can sort of see that those loops correspond to foot points of opposite magnetic polarity. So that's kind of cool. So I'll say a few words about solar chromosphere. You know, it's been studied primarily at optical and ultraviolet wavelengths, which, you know, they've learned a great deal. It's very powerful techniques, but, you know, they generally form under conditions of non-LTE, non-local thermodynamic equilibrium. The radiative transfer is complex. It involves nasties like resonance scattering, which can be used to advantage. For example, the Hanley coherent scattering can be used as a diagnostic. Partial frequency redistribution, non-equilibrium ionization, and so on. As I hope I conveyed, that millimeter or radio in general, the radiative transfer can be quite simple. We're in the Rayleigh-Jeans regime. For the optically thick case anyway, you have a nice linear thermometer of the medium in question. But the chromosphere, it's a real headache. It's a very complex environment. Onset of non-radiative heating, right? Temperature's going up. Why would the temperature go up when you have an ice cube of 6,000 degrees on one side, cold interstellar space on the other side? You know, complicated processes lead to non-radiative heating. Waves, shocks, mass motions. There's a transition from the dominance of gas pressure to magnetic pressure, so-called high beta to low beta. Transition from low ionization fractions to high ionization fractions. So it's a very complicated environment that we don't understand, and we were discussing yesterday during coffee that, you know, a lot of attention and time has gone into the coronal heating problem, solar wind heating and acceleration, momentum deposition, but really the action is in the chromosphere. It's a huge problem in trying to understand the energy budget, the energy transfer, the structure, the dynamics, and so on. An example, spicules. The idea that spicules, these are just little slender jets that you can see. They were discovered by a Jesuit priest back in the 19th century. But for a long time, people suspected they may play a role in providing mass and energy to the sun's atmosphere. If you look at the mass flux at, say, a few megameters above the surface of the sun, it's 100 times what's needed for the corona in the solar wind. Okay, so, and this, sort of was revived during the Hinode and Iris era, and we sort of took a look at them using ALMA. Why? Because they're simple to observe. What's shown here is spicules at 3 millimeters to the left. You see that they're an absorption at 171 angstroms observed by SDO in the middle, and you see the Iris magnesium 2 observations at about 10,000–15,000 degrees on the right. We sort of did a statistical study at 1 millimeter, 3 millimeters. You can scale because of the wavelength dependence of the opacity, the wavelength square. We can measure the opacity as a function of height. And it turns out, in our case, the density inferred is very insensitive to the temperature of the spicule. We see everything that's there from 10,000 degrees up to coronal temperatures because we have this very insensitive dependence of T to the quarter. So we looked at mass flux as a function of height, and we found actually that it's not sufficient to feed the corona. The amount of mass flux getting up to coronal heights is insufficient, was our conclusion. Okay, I'm going to move upward in wavelength, downward in frequency, and say a few words about a couple of phenomena. These are slides, complements of CGU at NJIT. There's a nice active region seen in the optical sunspot. You can do the magnetic field extrapolation. You see this nice sort of bipolar configuration, lead spot following. And sort of to the right there is the extrapolation. You see the field extending up into the atmosphere. And at a given height, there's going to be some resonant layer, some multiple of the local electron gyro frequency. Okay, so this is the S=2 layer, which is at 500 Gauss, if you're observing at a frequency of 2.8 gigahertz S-band. Okay? And what you find, and it's shown in the figure here on the left, is that in fact it becomes optically thick on this iso-Gauss layer. Okay? And if we go up to the S=3 layer, the harmonic number, 3 times the local gyro frequency, which corresponds to a local field of 333 Gauss, you have a higher iso-Gauss surface shown on the lower left there. Okay? So you sort of think of it as layers of the onion. As you go to higher frequency, you're sort of penetrating deeper into the onion. And so it also suggests a possible tool for measuring magnetic fields at coronal heights in active regions. Okay? Now, it turns out that the opacity of gyroresonance absorption depends on line of sight. It's very sensitive to the aspect angle relative to the magnetic field. So there are sort of holes in the opacity. So at the S=3 layer, for example, you have a hole that's bigger than at the S=2 level. And so you might, depending on your viewing angle, see right through S=3 layer down to S=2. If there's a temperature gradient, you'll see a great big, strong, circularly polarized signal. That's kind of illustrated here. And if you sort of take a cut through these layers of the onion, you see that, we have this layered onion effect. And this suggests that if we have an instrument that you can image as a function of frequency and space, or angular resolution, you can sort of tune up and down the dial and tune through these iso-Gauss layers. Okay? So we've done that a decade ago, I guess, tracking an active region across the solar disk, observing it with a VLA from 1 to 8 gigahertz, and you can sort of see selected frequencies and times to the right there at 1.4 gigahertz, 20 centimeter wavelength. Free absorption is still very much a factor. Yes? I'm sorry, could you repeat that?
So these
in terms of the schematic that I showed, those surfaces correspond to these resonant layers. So the magnetic field where those surfaces cut across the field lines are identically 500 Gauss or 333 Gauss. The field lines were just, yeah, force-free field extrapolations for the illustration of what we're trying to say here. I mean, potentially, you can use this technique, and this is a research frontier, is how do we exploit this, what is intrinsically 3D information to say something about the field, currents being carried by that field, and so on, and where heating is taking place locally, where it's being dissipated. So, I mean, I think it's a really exciting prospect, but the tools just aren't there yet. And this is just sort of a crude example using the VLA of, we sort of transition from free to, you know, the rightmost vertical columns day by day of the gyro resonance emission we see over the sunspots. And this is sort of the full sweep, 1 to 8 gigahertz of the emission that we see. So you see at low frequencies that we start, it's the fluffy free stuff, and then quickly that becomes optically thin because as you increase frequency, optical depth drops for free. And we're totally dominated by the gyro resonance emission. And suppose you take a cut at a constant brightness temperature at the base of the corona, say 10 to the 5 Kelvin, well, then you can get a coronal magnetogram at that height. Okay? Or a proof of concept. Yes? As we increase in frequency, we're penetrating deeper in height into the active region, but it's sort of a non-linear height because really what you're seeing is a map of brightness temperature as a function of magnetic field. So you need to break that degeneracy and understand both the brightness as a function of height and the magnetic field as a function of height, and there are various tricks we can talk about if you want. Okay, I'm gonna pivot now to non-equilibrium distributions of electrons, still incoherent emission, but flares, okay? Turns out centimeter wavelength emission is particularly interesting. It's been used for many years to study energetic phenomena. This is, you know, by microwaves, I mean sort of few centimeters up to, about 30 centimeters down to a centimeter or so. And in this case, the energy of the emitting electrons is sort of hundreds of keV to MeV energies, okay? So you're getting into the high energy tail of the electrons accelerated by energetic phenomena like flares or CMEs. And they're very closely related, very complementary to hard X-ray and to some extent gamma ray radiation. And so, you know, shown in the lower left there are light curves in both hard X-rays and in microwaves. You see the similarity. And this famous figure from 1988 by Kasugi shows the correlation between peak flux in 17 gigahertz microwaves and the hard X-ray peak count rate. So these are closely related emissions. They're completely different mechanisms that I'll show in a bit more detail. And they have very different dependencies on the population of emitting electrons. And that's why they're so complementary in sort of getting a handle on the physical processes responsible, because they have very different dependencies on the background thermal plasma, on the temperature of that plasma, the magnetic field strength and its orientation, and the distribution function itself of the emitting electrons. So here's a cartoon, which I think is still relevant, from Marcus Schwandan and Arnold Benz, where we have, you know, it's a black oval here where particles are accelerated. What happens to those particles? They stream away. They're energetic. They can be tens of keV on up to MeV energies. Microwaves occur below in stronger magnetic fields here. They stream down. Those with small pitch angles precipitate from this loop system and strike the chromosphere, which is a cold target. So you have fast non-thermal electrons producing thick target, so-called thick target hard X-ray emission. Okay? And you have the same population of electrons trapped for a time, producing microwaves. The thick target emission corresponds to foot points where the plasma is rapidly heated. It boils up through ablation, or so-called chromospheric evaporation, producing soft X-rays in the loops. And you also have electrons streaming outward, producing so-called decimeter meter wavelength radio bursts that I'll talk about. Okay, when you inject fast electrons into a converging magnetic bottle, you have a magnetic trap, and the electrons with large pitch angles bounce back and forth and bounce and forth. Those with small pitch angles bang into the chromosphere, producing these hard X-rays rather promptly. And you can sort of think of it as this schematic thing: acceleration, injection, propagation. Some fall out directly, some bounce back and forth, but ultimately electrons lose energy and are lost from the trap. They're thermalized and so on. So here's an example. Here's a movie of a flare near the limb from Nobayama. It's quite pretty. It's 17 and 34 gigahertz. You're seeing the glow of MEV electrons trapped in magnetic fields. Okay. And on the right there, you see the corresponding hard X-ray emission. The contours being the high energy non-thermal foot points, and the sort of fluffy color there is thermalized electrons. What I like about this movie is at 34 gigahertz in particular, you'll see, the non-thermal horns, and then you'll see things as they thermalize and produce this sort of beautiful cusp-like structure between those non-thermal horns. So, we sort of have this situation going back to the cartoon, the non-thermal radiation microwaves from the legs. There are lots of things you can do. With spatially resolved observations, it's kind of interesting to look at the light curves as a function of space and time. At the foot points, you find that the delay between the microwaves and the hard X-rays is shorter than at the loop top. Why is that? Well, you have to look at the variation of the emissivity as a function of magnetic field. It depends strongly on the magnetic field. So higher the field, the higher the emissivity and the higher the peak for the spectrum. You can sort of think of a magnetic loop, which has strong magnetic field at the foot points, weak magnetic field at the loop top, is a dispersive element. In other words, where the field is weak, if you're observing at a fixed frequency, you're seeing higher harmonics and therefore higher energy electrons than at the foot points where the field is strong and you're looking at low harmonics, lower energy electrons. So low energy electrons thermalize faster than high energy electrons. So you have less of a delay between hard X-rays and microwaves near the foot points than at the loop top. Now there are various dependencies. The spectrum, the non-thermal gyrosynchrotron spectrum is very rich. It has dependencies on, as I mentioned, the thermal background plasma. It also has unique dependencies on the details of the electron distribution function, the natures of, the power law tail, where it cuts off, and so on, and the magnetic field orientation, which is why we also need polarization measurements. People have been busy over the past decade doing forward modeling, because this is a very rich spectrum, and you can extract information about particle transport, ultimately the goal being particle acceleration mechanisms. And so this toy instrument, Pathfinder instrument, the expanded Owens Valley Solar Array, which is just 13 antennas, but it does sweep from 1 to 18 gigahertz, has been used in recent years to do just that, to do forward modeling and extract these various parameters which evolve in time and space using observations across a broad band. So they might not look like much, but there was this very nice flare, the celebrated flare, big X8.2 flare, for those that has some meaning to. It's a big flare, right on the limb. It was a theorist's dream, really, if you look at the movies. It's really quite remarkable. And Owens Valley was able to image the thing as it evolved over the course of about an hour from 1 to 18 gigahertz. And what they were able to show, and I'm not going to go into details, I can refer you to the paper if you're interested, shown in the sort of upper right here, is the run of magnetic field in that current sheet extending behind the eruption, the flux rope that erupted in the course of this flare. They were able to use the imaging spectroscopy of the gyrosynchrotron emission to constrain the magnetic field in that current sheet and estimate the dissipation of magnetic energy during the course of that flare. So these are really quite powerful techniques. Okay, let's move on in wavelength, going to longer wavelengths still, so decimeter wavelengths, tens of centimeters of wavelength. Thermal free-free plays a role, non-thermal gyrosynchrotron. Now we're beginning to get into coherent emission mechanisms. In spectroscopy, we've known for many years that you have upward-directed beams, downward-directed beams. So non-thermal electron beams zipping along the magnetic field, exciting plasma radiation, these electrostatic oscillations. Here's an example, again from the VLA, where we were clicking away at 50 millisecond time resolution in both polarizations. So this is the dynamic spectrum. You see the hard X-ray and radio light curves on the bottom there. And this was not a flare, this was a jet eruption. So pretty tiny, pretty simple. And we made a movie. If it goes. Oh no. Did not go. That's really too bad. Oh, thank you. You'll see the, whoops, still didn't go. Well, if the movie goes, you'll see that the red contours are where the electrons splash down, making the hard X-ray emission. And if the movie goes, you'll see what looks like a little lightning storm. It just flickers, very fast flickers over time. But if we gather up those flickers, yeah, I can show it to you offline. If you gather them together, you have this sort of nice cusp-like structure where it's color-coded, red is high frequencies and blue is low frequencies as you're tracking the trajectories of these beams, leaving where this magnetic reconnection event took place and produced this soft X-ray jet. And if you go through the arithmetic and look at the EUV data, you find out actually this being plasma radiation, the corona above the active region is extremely fibrous. In other words, it's very high density, very low density with some filling factor is the way the structure of the corona manifests. Moving on to yet longer wavelengths. I'm running out of time, I see. No, I'm not. Still have half an hour? About a half an hour. Okay, good. This has received lots of attention over the years. Meter wavelengths is really where solar radiophysics was born because the techniques were fairly straightforward to implement. And unfortunately, it's one of the most complex domains that one can possibly hope to study. We do not understand solar radio bursts. It's my claim. You've all, as I said earlier, you've probably heard of the classical radio bursts and type 1, type 2, type 3, et cetera. It's basically just the order in which the phenomenon was discovered and characterized in dynamic spectra at meter wavelengths, mostly in Australia, to some degree in France. So type 1, discovered in the post-war years, 47 I think was when the paper was published. We don't understand type 1 still. It's believed to be plasma radiation at the fundamental, but the microphysics that creates the plasma waves, it's long-lived, it can last for hours, even days. It can be 100% polarized. We still don't understand the microphysics in my view. Type 3s, of course, have been a workhorse. They've been studied for many, many years. It's been a cottage industry. People have made their livelihoods on type 3 radio bursts. Non-thermal electron beams propagating up and out, down the density gradient into the interplanetary medium. So they're seen in the corona, they're seen extending all the way out to the interplanetary medium to 1 AU and beyond, okay? And I'll come back to type 3s because they have their uses. Type 2 and type 4 are often paired, like any good meal. You have a type 2, which is a shock-driven disturbance in the sun's corona. And that is this part here, often occurs in 2 lanes corresponding to fundamental and harmonic plasma radiation. And it's often followed by so-called type 4 emission, the afterglow. And there's still some controversy over the nature of type 4 trapped energetic particles. And then finally, type 5, which is barely discussed these days, is often paired with type 3 radio bursts, typically polarized in the opposite sense. Somewhat more recently, 25 years ago now, synchrotron radiation from CMEs was discovered, which is pretty exciting. So this is an animation at 420, well, it's the observations, a movie at 421 megahertz made by Dalmiro Maya and colleagues in 2004, fast CME accompanied by an SEP event, solar energetic particle event. And the fact that it's synchrotron radiation gives you some hope, given full polarimetry, and we don't have an instrument that will do that. Possibly LOFAR, but the resolution is not very good. But getting up to sort of half a gigahertz, doing polarimetry, you have some possibility of getting a handle on the orientation of the magnetic field in that flux rope as it propagates out in its earliest stages. Why? Because you have linearly polarized radiation from synchrotron radiation from the flux rope. More recently, using low frequency instruments that I've mentioned, the MWA, the Owens Valley long wavelength array, people like Mondal and colleagues have been looking for lower frequency manifestations of synchrotron radiation from CMEs, so radio CMEs, we'll call them radio CMEs. And you'll see that, the flux densities typically are quite low. They're very faint relative to the coherent radio emission that they're often accompanied by. There are a couple of outstanding examples that puzzle me, way up here, very high flux densities, relatively speaking. Now let's jump up above the ionospheric barrier to space-based platforms. You can do radiodynamic spectroscopy from space. It's been done for years, and classical radio bursts, predominantly type 3 electron beams, but also type 2 has been studied. And what's nice in recent years is you have multiple spacecraft that are kitted out with spectrometers. So Parker, Solar Orbiter, the stereo spacecraft, wind waves. So they have different perspectives from different locations within the inner heliosphere on these radio bursts. And so here's an example. Let's see, the location of 3 different spacecraft plus the ground-based LOFAR observations is shown in the upper left there. And they observed a type 3 from all these platforms. They were able to triangulate using them and basically map the trajectory of the non-thermal electrons out into the interplanetary medium. Pretty cool. And finally, all the way out at the very boundary of the solar system, the heliopause, there was a remarkable paper published by Don Gurnett back in 2003 who pointed out the recurrent emission occurring down, look at the frequency scale, 2.5 kilohertz. You can figure out what the local electron density is. At Earth, it's what, about 10 per cc? So, local plasma frequencies around 20, 30 kilohertz. So way further out at the very bound of the solar system. And what we see at each solar cycle, this sort of accumulated impact of disturbances like CMEs, et cetera, moving out during solar maximum and eventually colliding with the boundary of the solar system, the shock there. But there was a sequel to this, in 2021, just 5 years ago. The Voyager 1 went into the interplanetary medium, the interstellar medium. It passed out of the heliosphere into interstellar space back in 2012. And you can sort of see the galactic cosmic rays, this great big jump right here in 2012. And kind of remarkably, you see radio bursts continue to occur So somehow the sun is making its influence felt out into the interstellar medium. And sort of the cartoon they proposed is that you sort of have an electron foreshock that allows these events to occur. I think one of you, during your elevator speeches, indicated you're modeling the shock way out here. There. So anyway, I find this really quite remarkable. Okay, just to conclude, there is a mission I mentioned earlier called Sunrise, which is going to send 6 little spacecraft up with long whip antennas to do imaging spectroscopy at very long wavelengths above the ionospheric cutoff. And this is sort of a proof of concept mission, but the basic motivator is to observe type 3 and type 2 radio bursts and follow their trajectory using basically source centroid. We can't really image it as it moves out from the sun. And doubtless also Jovian radio emission and things like that will be seen as well. I showed this slide a year ago, and it's exactly the same slide. It also said launch imminent. It still hasn't left the ground. Cross your fingers, I think it'll be quite interesting. All right, I'm going to spend the last bit of time on propagation studies. So we're going to turn things around, and instead of looking at emission, radio emission that is intrinsic to the plasma, to the corona, chromosphere, whatever, we're going to use various kinds of probes whose properties we think we know something about to say something about the medium through which the radio waves propagate. So one such technique is using radio bursts themselves, right? They propagate out into the interplanetary medium, and we can use the way those radio waves propagate to us, the observer, to say something about the intervening material. We can use a spacecraft beacon, okay? So Messenger spacecraft has been used this way. Various others have been. In a couple of instances, even radar has been used, transmitted from the Earth, in fact, using Arecibo, bouncing off Venus at superior conjunction and back through again, so double pass through the medium. Or you can just do something very simple, use background sources like a quasar, a blazar, active galactic nucleus, which are point-like, spatially coherent sources to transilluminate the foreground medium, okay? So this approach, using radio bursts, has been used for literally decades, since the late 60s, using basically photon diffusion codes, forward modeling codes, and try to deduce how the emission is affected by inhomogeneities in the corona and solar wind. And then I'll say a few words about this other approach, which is basically using the tools of statistical optics to say something. We have this point-like source illuminating with plane waves the foreground medium. So here's a little bit more background. This is the end, I promise. But if you have a plasma and electromagnetic waves propagating through that plasma, in vacuo it's omega squared equal k squared c squared, but in a plasma you have, in the unmagnetized plasma, you have this additional plasma frequency squared. And so the refractive index is actually not unity, as it is in vacuo. It is square root of 1 minus observed frequency over plasma frequency squared. So you can see right away that the plasma frequency is related to square root of the electron number density, and therefore fluctuations in the refractive index, which affects propagation, is related to fluctuations in the electron number density. Okay? Right away you have a direct mapping. You can write a 2-point correlation function for fluctuations in the refractive index, or equivalently, the electron number density, okay, which I do there. And these are all sorts of subtleties we could argue about, but for a homogeneous isotropic medium, the 2-point correlation functions only depend on differences in coordinates. And you can take the Fourier transform, and now you have a spatial spectrum of the electron density fluctuations, or equivalently, the refractive index fluctuations. So, these calculations go way back. Here's an example. Well, one of the seminal papers was by Jean-Louis Steinberg back in 1971, who assumed the density fluctuations could be described by a Gaussian correlation function. And if you go through the arithmetic, you find that the angular deviation caused by these fluctuations in electron number density go as a strong power of the electron density fluctuations themselves, the scale of the fluctuations, and the refractive index to the fourth. So things like plasma radiation have a very strong dependence on the refractive index. It's nearly zero. Right? So a whole lot happens to smear out the signal close to the source. And then as the refractive index goes towards unity, things sort of straighten out. But you'll see that the properties of the medium are embodied by this epsilon squared over h, the scale of the fluctuations. And sort of more modern incarnations, I mean, the same basic approach is still used even now. Proponents are people like Edward Kantar and colleagues. They use a stochastic Fokker-Planck formulation, sort of a Monte Carlo-esque thing to sort of track photons to a distant screen. You can sort of take the moments of that distribution to say what the source will look like. We know the correlation functions are not Gaussian. They're sort of better described by power law, or power law with breaks in it. And the analog now to the epsilon squared over h is this sort of spectrally weighted wave number. So, people have been using these forward modeling codes to model basically the apparent location and the relative time delays at various frequencies for type 3 radio bursts. And they use that to constrain the density fluctuation spectrum. Okay? And I can, again, provide you with details. Preliminary Parker results indicate sort of relatively high density fluctuation, sort of in the range of 10–20%. In the inner corona, I would dispute that, actually. Tiny bit more background. If you have a radio wave propagate through a plasma slab of thickness delta Z, relative to in vacuo, it's going to be delayed slightly. And you can estimate that time delay through this expression delta Z times 1 over the group velocity minus 1 over velocity of light in vacuo. And that's referred to as the group delay time. And it's related to this thing called the dispersion measure, which is just the line of sight integral over density times wavelength squared. So this has been used for very simple experiments, again using spacecraft beacons, to measure, put constraints on the line of sight density through the corona. And that's shown by this paper by Bird et al. In 1994. But it's also interesting to point out that for this plasma slab, the phase of the incident wave is also changed. Okay? And so delta phi, the change in phase, is just proportional to wavelength times the slab thickness times delta n again. So now we have a direct relationship between delta phi and delta n, and a very useful statistic is the so-called wave structure function, which is just this difference in two-point correlation functions. And we can measure that. Okay, this is an example of the effect of dispersion on the signal, this time delay, as a function of frequency. And this is for a true sort of impulse burst called a fast radio burst, which is thought to be cosmological in origin. So there's lots of excitement out in the community using fast radio bursts as a cosmological probe. Different story, but very vivid illustration in the dynamic spectrum of what that dispersion measure sweep looks like in terms of delay. Okay, so here's a cartoon showing how we might use a background point source to do something very simple. Basically, we can measure with a radio interferometer something called the mutual coherence function, which is just the second order statistic of the incident electric field normalized. That's what an interferometer measures. Now, most of what we look at is not unresolved point sources. We look at radio galaxies, supernova remnants, things like that. We refer to the measurement as a visibility, complex visibility. Making a whole bunch of such measurements, we can do the inverse Fourier transform and get an image. Well, in the absence of any scattering any intervening medium. We look at a point source. Basically, all interferometers see the same thing. They see an amplitude of 1 and a phase of 0 for a point source normalized by its flux density. But if we have an intervening medium, say the solar wind moving out, due to the phase changing properties of this inhomogeneous plasma, what comes out is a corrugated wavefront. So defining the sort of angle of arrival as the normal to that wavefront, corrugated wavefront, you can gather up those vectors and voila, you have an angular spectrum. In other words, that background source has been smeared out by the foreground medium. Okay, that sounds kind of boring, but it turns out there's actually quite a bit of information crammed into this thing we call the structure function, which is related to the mutual coherence function in a very simple way. Mutual coherence function, it turns out, is related to e to the minus ds over 2, ds being the structure function, which is, we measure it directly with a pair of antennas. It's a very straightforward measurement. Now, because you have an angularly broadened source, you also have multiple angles of arrival, which means automatically that you're going to have temporal broadening, which is order of magnitude given by distance to the screen, theta squared being the angular size of the source, gives you sort of the time delay or broadening. And you also have, in the presence of a moving screen, spectral broadening. All of these can be leveraged to learn something about the medium. Also, you can look at fourth moment statistics of the electric field, intensity. So, intensity goes as electric field square, and so you're doing correlations with intensities, looking at scintillation. It's much hairier to interpret IPS in practice, but it's also been used for many, many years by people going all the way back to Tony Hewish, who got the Nobel Prize with for discovery of pulsars, a sensitive topic. But he did do some pioneering work on IPS. Basically, you can sort of think of the screen as making all these little diffraction cones. The emission is forward scattered into these cones, which propagate to the ground and interfere with each other constructively and destructively as the solar wind screen sweeps over the ground, and you see intensity variation. So right away you can see you could probably measure the solar wind speed with a suitably arranged, oriented pair of antennas by just cross-correlating the scintillation pattern, right? I'm not going to really talk about that. One other effect, Faraday rotation, was mentioned yesterday for a linearly polarized background source. Coming through the foreground magnetoactive plasma, the electric field vector of that linearly polarized radiation is going to be rotated by an amount given by that integral expression there. And you'll see that under the integral, in the absence of B, you just have dispersion measure. In the presence of B, you have a B dot Z, so that's the line of sight component of the magnetic field. That integral expression with the constants is called the rotation measure. And again, there's a wavelength square dependence. So in principle, you can leverage information about the magnetic field in the medium using Faraday rotation measurements or Faraday fluctuation measurements. So there are lots of remote sensing propagation phenomena that you can leverage to learn something about the solar wind, the solar corona, solar wind turbulence, and so on. I'm going to just close things out with a few words about sort of one of the simplest propagation effects, this angular broadening that I mentioned, and then I'll say a couple of words about Faraday rotation. So solar wind spectrum, again, this goes back in the Wayback Machine, many years. It's been studied. What's shown from a review from Lepping is the basic sort of time average magnetic trace spectrum for fluctuation spectrum for turbulence in the solar wind, an energy containing scale, the classic sort of Kolmogorov-like scale, and then some break to a dissipation scale. The density, the corresponding density fluctuations have a similar spectrum in some sense. I'm showing the structure function here, but basically think of it as the power spectrum flipped around. It's Kolmogorov-like at the large scales, but then it inflects up to something flatter. There's more power and density fluctuations than you would expect from just a pure Kolmogorov shown in the dashed red line. And then it too breaks down at some scale. So there's been a lot of interest, especially with Parker and Solar Observer out there, Solar Orbiter out there. And particularly, there's a lot of intense interest in solar wind turbulence near the dissipation scale. And I think somebody else in this room is working away on that particular problem. I mentioned the tools of statistical optics can be used, use background sources. It turns out that the structure function that I've mentioned is related to this spatial spectrum of electron density fluctuations through this integral expression, given those assumptions that I mentioned earlier. We need to assume some functional form, which often use a power law with a cutoff at some dissipation scale, in which case you get a solution which is closed. It's in terms of a Kummer function, the 1F1. It's a hypergeometric confluent hypergeometric function, which is a $10 word for a very simple function. I've done some work in the past looking at lots and lots of background sources through the corona during solar minimum with the VLA. So basically you're measuring the structure function on scales of hundreds of meters in the corona to tens of kilometers, okay, right in this sort of dissipation regime. And this is what the data look like. In the left-hand side, in the upper left, is what the normalized visibility data look like. That's the mutual coherence function. But if you take the inverse Fourier transform, you get the image, the scatter-broadened image, in the color panel there. And you see that it is anisotropic, and the arrows are pointing back at the sun. So it's scatter-broadened perpendicular to the radius to the sun, which has been interpreted for many years. It's basically saying the scatter broadening occurs perpendicular to the magnetic field. Why? Because the density inhomogeneities are elongated parallel to the magnetic field. So we can fit the coherence scales where structure function has a value of unity, 1 radian squared, normalize our visibility data. That's what the green points are. Take -2 log of that, and we get the structure function. So it's a pretty direct measurement of the structure function. And there's the, in dark blue there for different values of alpha. That's what the model structure function looks like, the Kummer's function. And so we can fit to our data both the power law index, which is much flatter than Kolmogorov, and the break scale. And if you plot up the break scale, we find using interferometric techniques that we get something very similar to things that have been done in past years using spacecraft techniques, spectral broadening, and IPS. And what we find, in agreement with previous authors, is that the break scale in density is very close to the ion inertial scale. This is where electrons and ions decouple, which for low beta plasma turns out to be very close to the ion cyclotron resonance scale. Now that's a conversation we can have offline. I think it's very interesting because such a break is also seen in fast solar wind in the magnetic spectrum at that same scale. Faraday rotation. Last couple minutes on Faraday rotation. Again, this is a technique that's been exploited for many years. This is from a paper by Petzold back in 1987, where the Helios spacecraft was used to illuminate with a linearly polarized beacon the foreground corona, and they measured the Faraday rotation through the quiet corona. And because the field is going to be quite variable in the corona, they are able to basically define an envelope of such measurements and use that to deduce an envelope of the coronal magnetic field. So I think Doug mentioned coronal magnetic field measurements yesterday. There are more than one way to skin a cat. You can use the gyro resonance techniques for strong fields. You can use thermal free-free for weak fields. You can use Faraday rotation for even weaker fields and further out into the corona. Of course, the downside of this is that you really only have a single pierce point and you accumulate such measurements over time. What you'd really like is a technique that will measure magnetic fields in the corona comprehensively as a function of space and time. Faraday observations of magnetic flux ropes have also been attempted with some success. A couple of techniques, again using background sources, but instead of point sources, you use a background radio galaxy because the lobes are synchrotron radiation, they're linearly polarized. So you observe it and map the electric field vectors when there's no solar wind in the way. And then as the sun passes in front of the radio galaxy, you look at systematic deviations of those electric field vectors due to Faraday rotation and are able to, through modeling, place some estimates on the magnetic field and density along the line of sight. So that's been done by people like Steve Spangler and his student, Jason Cooey. Or you can measure using, again, spacecraft beacon. So people like Liz Jensen, Russell, and others have done such things. There's a very nice piece of work by Wood in 2020, which did forward modeling of such observations. So looking at the white light CME, the model, looking at the Pierce points using various instruments, and you see that the rotation due to Faraday rotation is fairly faithfully reproduced. So, there's some promise there as well. So that was, I realize, a whirlwind tour of the kinds of things we can do. I'm going to stop now. So thanks.
All right, we got a couple of minutes for questions for Tim.
Sorry, I'm just not sure. So can we use this radio transmission technique to map the magnetic field structures in the solar wind? Because my understanding is that the current stage of global modeling assumes that magnetic field lines follow Parker spirals, and so which is not the most accurate thing to do. So I'm wondering if this can be used as a constraint.
Well, I ran through a couple different techniques to constrain the field in the corona itself. I assume that's what you're referring to, well above the surface.
It could be at the base of the solar wind, then, yeah.
So basically, the gyroresonance mission sort of allows you to do some forward modeling and constrain the magnetic field as a function of height in active regions. It doesn't really tell you much about what's going on higher up. In terms of the Faraday rotation work, that has typically been done at 10 to 40 solar radii out. And you have to realize that you're looking at a projection of the magnetic field on the plane of the sky. So there's this line of sight integral that's density weighted that you're constraining, which is why you have to use forward modeling, the Enlil model or something else to sort of get a handle on what the density distribution might be like along the line of sight and what the field is doing along your line of sight, the line of sight component of the magnetic field. And so by iterating, using that model as a starting point, you can perhaps place some constraints on the magnetic field just along that one Pierce point. Now for the radio propagation measurements, I just showed you an example of one point source that's angularly broadened, and it's broadened perpendicular to the magnetic field. If you have literally tens or hundreds of such measurements, you could map the orientation of the field on the plane of sky. And that might be useful. But again, when you sort of think of Parker spiral, you're looking down on a projection in the ecliptic of the field being wrapped up in some way. So yes, it can provide some constraints out. And ideally you'd have frequency coverage. It goes to lower and lower and lower, so you can go further and further from the sun and see what it's doing. But certainly, between 5 and 10 or 20 solar radii, it's very highly aligned with the coronal magnetic field.
So, do you observe these free brainstorm emission only from thermally driven wind in sun and sun-like star, or say, for example, if the wind is alpine wave driven wind or dust driven wind, how large or small are these free emission?
Well, the corona is, that's a good question, because you know, the temperature of the ions is not necessarily the same as the electrons. At radio waves, we're looking at the electron temperature. As we tune down in frequency, the free emission becomes optically thick, higher and higher up in the corona. But these pesky propagation phenomena, they can be a blessing or a curse in the sense of making direct measurements of the brightness, the electron temperature as we go up in height. As we get to, say, 100 megahertz or so you're still, what, maybe a solar radius above the photosphere, 1.5 solar radius out. Basically, the rays are increasingly affected by propagation and refracted, so you get this strongly suppressed disk center brightness, and it's suppressed even further as you go to the limb. So it's not a reliable proxy for kinetic temperature as you go down in frequency, unfortunately.
I was wondering, when you were showing those pictures for the flares, you could very clearly see like a, like typical loop-like structure, but then there was something like that was a little bit more elongated, a little bit like more towards the bottom of the image. I was wondering if you could comment on what that is.
Yeah, that was kind of cute, because the movie I showed you is 1 frame per 10 seconds for a couple of hours. So it was a so-called long duration event, eruptive, with things raining back down for quite a while. And it's basically a filament eruption that occurred late in the event, and you saw that it actually absorbed the background emission. There was this dark thing that passed by, and then there was this little magnetic disconnection event that you saw a bright flash, and the whole image jittered because it's a self-calibrated image, and it goes with the centroid of the emission. So when a bright spike went off, it torqued the position of the map. So yeah, good eyes.
So like shock is like a thin 3D structure when we are measuring type 2 radio burst. So I was just thinking that those type 2 radio bursts are not coming from a centralized localized region of a shock. So it maybe come from this part and then this part. So how accurate is tracking those type 2 radio bursts?
That's a really good question. I would say that that's still in its fledgling. For much of its history, we have had no true imaging as a function of time of the classic radio bursts, a function of time and frequency. And so that's beginning to change now with instruments like LOFAR and NWA. You can, in fact, begin to track. But again, you have scattering phenomena, which smear things out a little bit, propagation phenomena, which it can affect the apparent position of fundamental versus harmonic emission and so on. But you're absolutely right that as far as we can tell, sometimes the type 2 is on the flank of a type 2. You want to have quasi-transverse shock for acceleration to reduce the plasma waves, but other people maintain, certainly by the time you get into interplanetary type 2s, it's more close to the nose of the CME. And that, I think, is something that's debatable and continues to be debated in the community.